All right, so now we're going to do a quick proof on Voronoi vertices and empty circles. So the theorem we're proving is a point V is a Voronoi vertex of the Voronoi diagram of S, if and only if there exists an empty circle centered at V that passes through at least 3 points of S and contains no points of S in its interior. This isn't too bad. So it seems like a lot, but it's not too bad. It's an if and only if. So we'll start with maybe this direction. Let's start. So we're assuming, let's see, assume that V is a Voronoi vertex. So that means that V is in at least 3 Voronoi cells. You sort of think about that visually, right? You've got your cells sort of coming together like this, and the point has to be in this cell, and this cell. If it's only in 2, then it's going to be on an edge or a vertex, but you know. Anyways, and you could also have more, right? Like we could possibly have 4, something like that, but at least 3 cells. So V is in at least 3 Voronoi cells. Let's say that those cells generators are, let's say S1, S2, all the way up to SK, where K is at least 3. So those are the points that are generating these Voronoi cells, wherever they are. So that means that the distance between V and each of those generators is going to be the same. I'm going to write that as the distance between V and S1 is equal to the distance between V and S2 is equal to the distance between V and SK. And maybe we'll define that to be equal to R. All right, so their distances are all the same. We're just going to draw a circle. So let's construct a circle of radius R centered at V. Since it's radius R, which is the distance between V and any one of those points, that means that each of those points has to be on the edge of the circle. So let's call this circle maybe C. Give it a name. So S1, S2, all the way up to SK are in the boundary of that circle. That's what that symbol means, in case you haven't seen that. That partial symbol in this context means on the boundary of the circle. And since there's no point closer to, well, if there was a point closer to V than any of those S's, then it wouldn't be, those S's wouldn't be, or like, I guess what I'm trying to say is V wouldn't be in the Voronoi cells associated with those S's. So that means there is no S star such that the distance between V and S star is less than R. So no, so in other words, the interior of C is empty. So we've finished that direction. The other direction, we're going to suppose that there is a circle C that passes through at least 3 points in S, or I guess in S, centered at V. All right, so we've got this circle. Let's let the radius be R. So we're just defining whatever that radius is to be R. And let's let those points be S1, S2 through SK, which are, as we said, in S and the boundary of C. So we know it's right on the edge of C. So we know that that circle is, we should also say that also C's interior is empty. Nothing inside, there's no points in S inside of C. So that means that the distance between V and each of those S's are equal. V is 2. Sorry, distance between V and SK equals R. And I guess somewhere here I should really write that K is greater than or equal to 3. So we got that far. And then that means that V is in the Voronoi cell centered at S1. And it's in the Voronoi cell, so maybe I'll write this as intersection. So we have this, which means that V is, what's that V? A Voronoi vertex. And that concludes our proof.